Hello everyone, welcome to the fifth lecture of week 1 of the course Process Equipment Design, and here we are discussing basic design parameters, and this topic I have started in previous lecture, that is lecture 4, where we have discussed different parameters which are involved in basic design equation of heat transfer, that is Q is equal to UA delta T Lm. So, we have discussed overall heat transfer coefficient, different terms involved in that, and the mean temperature difference, that is LMTD. So, what happened when I am designing shell and tube heat exchanger, I consider FT correction factor in log mean temperature difference, and that log mean temperature difference corresponds to the counter current flow. Okay. So, FT factor considers the mixed flow, because in shell and tube heat exchanger we have co-current, counter current as well as cross flow. All three pattern will occur simultaneously, and therefore we have to consider that through a mathematical term, and that is FT correction factor. So, in this lecture we will cover FT correction factor, its proper value, how to choose the right value of FT, and what is the consideration while choosing FT factor. And after that we will discuss fluid allocation to shell side and tube side, and then we will discuss some velocity as well as pressure drop limitations, okay, in shell and tube heat exchanger. So, let us start with FT correction factor. So, as far as FT correction factor is concerned, we consider that considering two different parameters. First parameter is thermal effectiveness of exchanger, and that we represent with P, and the ratio of two heat capacity flow rate, that is R. So, here we have two parameters P and R, and depending upon these two values we will consider FT factor value. Okay. So, what is this P and R? P is the thermal effectiveness of the exchanger. It means how effectively the heat transfer take place in an exchanger. So, obviously it will depend on the temperature difference. Okay. So, if I consider expression of P is basically THI minus THO, okay, and THI minus TCI. Okay. Now, if I consider this THI minus THO, that is the temperature difference of one fluid, that is the hot fluid, okay, and this THI minus TCI, what is this? THI minus TCI is nothing but maximum driving force or maximum temperature difference available in a heat exchanger, because highest temperature will be when hot fluid is entering, that is THI, and lowest temperature would be when cold fluid is entering, that is TCI. So, that is the maximum temperature difference available in the system, and THI minus THO is basically temperature difference of one fluid, that is the hot fluid. So, what I can say over here, that the maximum value of P should be 1. Okay. Maximum value of P should be 1, because in this case no driving force will be close to THI minus TCI. Okay. And further, if I speak about heat capacity flow rate, that is R, so that is CPH by CPC. So, TCO minus TCI by THI minus THO. Okay. So, this capital CP, this is not a small c, this capital CP is heat capacity flow rate, and that is the multiplication of M into specific heat, fine, of hot fluid as well as of cold fluid. Now, this is basically the combination of P and R. Okay. If I consider P as THI minus THO, can I consider P as TCO minus TCI divided by THI minus TCI? Okay. Instead of hot fluid temperature difference, can I take for cold fluid temperature difference? Definitely I can, fine, but in that case the combination will be for P but in that case the combination will be, for R we have CpC by Cph, right. So, whatever would be the numerator of P, okay, the same would be the denominator of R, that would be the proper combination. So, in some books you can find different terms of P and R, like TCO minus TCI divided by THI minus TCI, but in that case R would be CpC by Cph. Okay. So, this I am repeating because you have to keep in mind that this is not only the correct expression, other expressions are also there, but that should be in combination. And what is the combination, that I have already explained. Fine. Now, I will speak about that how we should consider FT correction factor. Okay. To explain that, I have to consider another parameter, and that we call as temperature approach. Fine. So, considering temperature approach, we usually have three basic conditions. The first condition is when we have sufficient temperature approach value. Okay. Now, what is temperature approach? Temperature approach you can see in this diagram, where I am having, this is the hot fluid, okay, this is the hot fluid where temperature decrement is there, and this is the cold fluid where temperature increment is there. So, temperature approach is basically the difference between outlet temperature of hot fluid minus outlet temperature of cold fluid, difference of this, difference of this. Okay, that is basically the temperature approach, as you can see here. Now, if this is the case, then I can represent FT factor in this diagram. This is the FT factor graph. You all must be aware with this, where on x axis we have p value and we have different lines, different curves for r value as shown over here. Okay. And we have given one factor, that is the FT factor. If it is equal to 0.75 or more, we consider that design is feasible, right. Now, how I can consider that design is feasible? Fine. Feasibility means what? When I am considering heat transfer, what is the meaning of feasibility? Feasibility means whatever would be the cold stream, okay, or whatever would be the temperature of cold fluid, that temperature will be less than the temperature of hot fluid all the time. Okay, then only natural heat transfer will take place. Okay, because it will definitely move from high temperature to low temperature. So, cold fluid temperature should always fall below hot fluid temperature. Fine. So, if you consider this diagram, here I am having a hot fluid, this is the hot fluid and this is cold fluid. So, at each point we have cold fluid lesser than the hot fluid, this much temperature difference is always there. Fine. So, this is basically the proper temperature difference, and heat transfer can occur easily, right. So, what is the point? That if I consider counter current flow, at every point cold fluid temperature will be less than hot fluid temperature. Fine. Now, what will happen in 1-2 shell and tube heat exchanger? Okay. If let us say instead of enthalpy, if I am considering here length, okay, if length is there and here I am having temperature also. So, if 1-2 shell and tube heat exchanger is there, what I can say, that terminal temperature should not change, okay, because whatever temperatures are available for hot fluid and cold fluid, that I cannot play with. Okay. So, if I consider 1-2 shell and tube heat exchanger, and if hot fluid is moving in shell side, right. So, shell side, because one flow is there, so it will enter here and exit at this point, right. Now, what will happen with cold fluid? Cold fluid will move in tubes, and that is 2 pass, right. But outlet temperature of cold fluid will remain at this point only. So, how this movement will occur along the length? First it will move like this, and then it will move like this, right. So, along the length in 1-2 shell and tube heat exchanger, the movement is like this. And further what I can say that at each point cold fluid temperature is less than the hot fluid temperature. It means at each point heat transfer becomes feasible. Okay. So, if this is the case, Ft factor will lie in feasible zone where Ft factor will be greater than 0.75. Okay. Now, why I have put the bar of 0.75? Because when I am considering LMTD for counter current flow, we multiply that with Ft correction factor, right, and that Ft correction factor reduces the temperature driving force, okay, reduces the mean temperature difference. So, if temperature difference will be reduced, area will increase manifold, right. So, to put a bar on area, we put a bar on Ft correction factor, because I cannot change LMTD, temperature I cannot play with. I can make a bar or put a bar on Ft value, and that value, that thumb rule is that it should be greater than 0.75. It does not mean that if it does not mean that if Ft correction factor reduces then 0.75, heat transfer will not occur. Heat transfer will occur, but the area will increase manifold. So, that we consider as infeasibility, right. So, if this is the case where temperature approach is sufficient, we can counter or we can consider proper heat transfer in 1-2 heat exchanger also, and therefore, in that case Ft correction factor will be more than 0.75. Okay. If you calculate, it will definitely come more than 0.75, because temperatures are like that. Okay. Now, further if I consider another condition, another situation, and another situation means what? When I am considering temperature cross. Okay. Now, what is temperature cross? Let us discuss with this. Temperature cross is basically when hot fluid exit temperature is lesser than the cold fluid exit temperature. When hot fluid exit temperature is lesser than the cold fluid exit temperature. Okay. In that case, what will happen? In that case, if I consider counter current flow, okay, if I consider counter current flow, or if you focus on this diagram, at every point cold fluid is lesser than the hot fluid. Okay. So, feasibility is maintained, but as far as counter current flow considers. Okay. If I consider, now if I consider 1-2 shell and tube heat exchanger and hot fluid is available in shell side. Okay. So, exit temperature of hot fluid will remain as it is, right. Now, what will happen with cold fluid? Cold fluid exit temperature is this. Now, if 1-2 shell and tube heat exchanger I am considering, and I am considering length on x axis, then this temperature should be allocated here. Okay. So, in that case what will happen? This first moves like this, and then it will move like this. So, what will happen in this region? Okay. Here we have higher temperature of cold fluid than the hot temperature, than the hot fluid temperature, okay, which is not feasible. Okay. However, we can consider some amount of temperature cross. Okay. In that case, if this situation arises, then what will happen? Ft factor will be equal to 0.75. Fine. So, what I can say that up to 0.75 little bit temperature cross is occurring, that is fine. Okay. Now, what will happen in temperature cross? Is it possible that cold fluid temperature increases than hot fluid temperature? Okay. In some cases you can argue that because there is a mixed flow, counter current, co-current flow. So, in some cases is it possible, but usually what will happen, it will not reach up to the desired temperature. cold fluid will not reach up to the desired temperature, it means desired heat transfer is not possible, and therefore, I am saying that temperature cross must be avoided. Okay. So, as temperature cross increases, FT correction factor falls rapidly, which is the infeasible design. Okay, because we should not allow temperature cross. Okay. So, I hope you understand that 0.75 is a bar, is a thumb rule to control the increment in heat transfer area, okay, and that will be due to the temperature cross. Okay. So, if we want to avoid the infeasible design, we have to avoid the temperature cross, and for that purpose FT factor should always be or equal to more than 0.75. Okay. Now, next is, if I am considering more temperature cross, then what will happen? Let us see. If you see this graph, here we have more temperature cross, up to this much temperature cross is there. So, as far as counter current flow is considered, I am again saying that no feasibility is occurring. Okay. However, in 1-2 shell and tube heat exchanger, we have this kind of flow. Okay. So, sufficient temperature cross will be there. Okay. So, sufficient temperature cross will be there, and this we are considering as large temperature cross. So, what will happen in that case? In that case, the FT correction factor falls rapidly and it will lie in a region of infeasible design. Okay. Now, my point is why this FT factor decreases. Okay. To explain that, let us compare temperature approach and temperature cross. Okay. Now, what will happen if I consider this diagram? Temperature approach is what? Temperature approach is basically this value. If I consider hot fluid temperature, so this is the outlet temperature of hot fluid and this is the outlet temperature of cold fluid. So, this difference is basically temperature approach, right. Okay. Now, if temperature approach is there, what is the P value? P value, if you remember, that is basically the inlet temperature of hot minus inlet temperature of cold. Okay. So, the difference is around this much. Fine. However, if I am considering temperature cross, then what will happen? This line will fall up to this level. Okay. And now, P value will be what? This minus this. So, what will happen? As temperature cross increases, P value will increase, right, because denominator value will decrease. Okay. Now, what will happen if I am considering same R? Okay, let us say this R I am considering, and if temperature cross increases, P value will increase. So, if I am operating over here and temperature cross occurs, so P value will increase. So, slight increase, let us say slight increase in P reduces FT correction factor rapidly, fine, because now it is falling in this asymptotic lines. Okay. So, as temperature cross increases, FT factor decreases rapidly, which we should avoid, fine. So, we will also discuss that what we have to do when FT correction factor falls less than 0.75. Okay. But first of all, you should understand that what will happen when FT factor reduces than 0.75, fine. So, in that case temperature cross increases, which we should avoid. Okay. Temperature cross, basically cold fluid increases than hot fluid. So, what will happen at that point, local reversal of heat transfer will take place from cold fluid to hot fluid, or in some cases cold fluid will not reach up to the desired exit temperature. So, all these infeasibility will occur when I am considering temperature cross. So, that we should avoid. Okay. So, FT correction factor says that the rule of thumb, okay, rule of thumb is what? Ft factor should be greater than 0.75 to consider practical design. So, if I am considering 0.75, that is okay, I have to do that, fine. Now, how I will do that? If Ft factor comes if Ft factor comes less than 0.75, okay, because I have already told you because I have already told you before that I cannot change the terminal temperatures. Whatever would be the temperature cross, I should not change the inlet and outlet temperatures. Okay. Then how I can improve Ft factor? Ft factor can be improved by considering more shell passes. Okay. Here what I have considered, one shell and two tube pass. Okay. And if one shell will remain there and I will keep on increasing tube passes, so hot fluid will pass only the shell once. Okay. So, no change will occur in fluid which is flowing in shell side. So, if I have to improve the temperature cross, I have to improve the shell passes. Okay. Now, I will discuss one example with the flow pattern inside the heat exchanger, so that you can get the idea that if I increase the shell passes, how Ft correction factor can be improved. Okay. Because whatever Ft factor graph you have seen till now, that is only for 1-2 shell and tube heat exchanger. If I consider 1-4 shell and tube heat exchanger, Ft correction factor graph will different than this. So, there we can find for the same terminal temperature, Ft should be more than 0.75, that is the advantage. Now, I will show the pattern that how Ft correction factor, how the shell passes improves temperature cross, and so the Ft correction factor. Okay. So, here I am explaining that with the help of this example. Here you see we have temperature and enthalpy profile where temperature cross is large. Okay. This much is the temperature cross. Okay. Now, if I draw that in 1-2 shell and tube heat exchanger, so you can understand here we have the schematic where fluid enters once to shell and exits, fine, and in tubes fluid will enter from here, it will pass through this and then it will exit from here. Okay. Now, what will happen? It will pass twice in tubes, fine. So, that you can understand from this graph there that you can understand from this graph that here we have temperature as well as length. So, in shell pass fluid moves once only and in tubes it moves twice. So, here I am having the temperature cross. Okay. So, this condition I should avoid. Okay. So, I will increase the shell passes, fine, and here we have the same condition like this. Okay. These two graphs are same, and here what will happen, instead of one shell we consider two shell. Here fluid enters in one shell, exits and then enters to second shell and then exits from second shell. And if I am considering two shell, I have to consider 4 passes in tubes. Okay. Once tube will be like this and then tube movement will be like this, right. So, here we have this kind of condition. Now, what will happen? I cannot change the terminal temperature, this temperature, this, all these temperature will remain same. So, when the fluid is entering, this temperature will be equal to this, you see, this is, okay. And then once it will exit the first shell, it will enter the second shell and then finally it will exit. So, this temperature and this temperature will remain same, fine. Now, what will happen with tube side fluid? Tube side fluid, this is the inlet temperature, this is the inlet temperature which is equal to this temperature, fine. So, and then it so the fluid starts from here and then exits in first shell, which is basically this shell, okay, and then at this temperature it will enter to the second, it will enter to the second tube at this temperature, okay, you see, and then it will move like this and then it will move like this, okay. So, what I can say that when I am increasing the shell passes, the movement of fluid will be like it will never cross the hot fluid, okay, because its path will change, fine. So, that is the advantage of increasing the number of shells. So, when I am increasing the number of shells, I am avoiding temperature cross, I am increasing FT correction factor, okay. So, when FT correction factor you have found less than 0.75, immediately you have to increase the number of shells. So, that is the basic design parameters. Now, we will consider another point, that is how I should allocate the fluids to shell or tube side, okay. Now, before considering this allocation, one thing you should keep in mind, that whatever verse you are doing, okay, whatever verse you are doing, that you should do with tubes, not shell, okay, you have to keep that in mind, okay. What is the meaning of that? If I have come across with some bad conditions, that condition I should allocate, I should consider in tube side, not in shell side, because tube side maintenance is very easy in comparison to shell side, and tube side, what I am saying, if I consider the cost also, so tube's cost will be very less in comparison to shell, because shell diameter is significantly large than the tube diameter, okay. So, that you should keep in mind, and then let me start with the factors. Based on that, we can allocate the fluid to shell side or tube side. The very first factor in that category is the corrosion, okay. What is corrosion? Corrosion is the phenomena when the reaction will takes place between fluid and the material, tube material or shell material, or we can say the metal, okay. So, there we have the rust formation, etc. So, it will weak the material, it will weak the equipment, okay. So, how I can consider that corrosion? Corrosion can be removed, corrosion can be eliminated considering special alloys, okay. So, if you are finding that fluid is highly reactive to the material, allocate that fluid to tube side, okay. What I have told, that whatever verse you are doing, just do it with the tubes, okay. So, high corrosion fluid should be allocated to tube side, and reason is very simple, that to avoid that corrosion we can use special alloys, and the cost of that material is very expensive. So, when I am preparing tubes with that material, it becomes cheaper in comparison to preparing a shell with that material, fine. So, high corrosion fluid should be allocated to, so high corrosion fluid should be allocated to tube side. Next is fouling, okay. How fouling will takes place, that I have already explained, it will depend on temperature and the solubility, okay. So, I am not going into detail of that. So, you should understand that the fluid is having either high tendency of fouling or low tendency of fouling, okay. How you can ensure that? You can see the dirt factor table which is with you, okay, in volume 6. So, the point is, when you are dealing with high fouling fluid, that should be allocated to tube side, because what will happen when you are considering the tube side, you can consider more velocity there, okay. And when you are increasing the velocity, it will take the scaled material with it, okay, which we also call as erosion, but erosion of the metal should not occur, erosion of scaled material should occur, okay. So, that we can control with increasing the velocity in tube side. Secondly, tube side cleaning is very easy in comparison to shell side, because tube side we have the straight pipes only, okay. So, straight pipe cleaning you can do easily in comparison to zigzag space which is available in shell side, okay. And when you carry out the design of shell and tube heat exchanger, you will see that space in between two tubes in shell is sometime lesser than the tube ID, So, you can see the high fouling tendency fluid should be allocated to tube side, okay, and reason I have already explained. Fluid temperature, okay, if fluid temperature is high, that should be allocated to tube side, okay. So, if temperature are high enough to require use of special alloys, placing the high temperature fluid in tube side will reduce the overall cost, okay. So, because of the same reason. So, how I am considering reduction in overall cost when I am considering tube or shell, okay. So, what will happen when this material will play a role, okay, it will play a role by making the uh, it will play a role by making the tube or shell. It means whatever would be the material involved in tube or shell, directly it will give the cost, okay. So, what will happen when I am saying the material so what will happen when I am saying the material involvement? It means the thickness of the material or thickness of the shell or thickness of the tube, fine. And how that thickness will occur? Again the same expression which I have discussed uh, in previous lectures also, that T is equal to P d naught by 2 F j plus P. So, here if I am considering same pressure and if I am considering diameter, so tube is having lesser dia, so it will have lesser thickness in comparison to shell. So, material cost involved in tube manufacturing is very less in comparison to shell. So, we can use costly material and alloys easily in tubes or in less price in tubes in comparison to shell. Okay. So, high fluid temperature should be allocated to tube side. Similarly, high operating pressure, that should be allocated to tube side, because high operating pressure or we can say high pressure shell is very costly in comparison to high pressure tube. Okay. In the same line as I have explained just now, that because pressure is constant, so thickness will be directly proportional to the diameter, and shell dia is very large in comparison to tube dia. So, high operating pressure should be allocated to tube side. Now, what will happen if I consider viscosity? Okay. So, generally the high heat transfer coefficient will be obtained by allocating more viscous fluid to shell side, okay. But this is with the condition that it should provide turbulent flow in shell side, okay. And in shell side flow is not straight, because we have different arrangement of the tubes. So, continuously zigzag motion will occur in shell side. So, turbulence in shell side is obtained at lesser Reynolds number in comparison to tube side, okay. Tube side, when I move tube side is basically straight pipe, and when Reynolds number exceeds 4000, it comes under turbulent flow zone. However, in shell side critical Reynolds number is around 200. If Reynolds number exceeds than that, we consider that as a turbulent condition. So, you have to consider the viscosity of the fluid, which must give Reynolds number more than the critical Reynolds number in shell side, and if it is appearing, you should allocate the fluid to, and if this is occurring, you should allocate the fluid to shell side, otherwise tube side. Okay. So, and next point we have about the stream flow rates. So, allocating fluid with lower flow rates to shell side will normally give more economical design. Okay. So, lower flow rate means lower flow rate in shell side means at low flow rate it gives the turbulent, and it will give better heat transfer coefficient. Okay. So, lesser stream flow rate should be allocated to shell side. So, based on this discussion, we have this order of priority to allocate the fluid. Okay. So, tube side corrosive fluid should be allocated, hot fluid should be allocated, fouling fluid should be allocated, less viscous fluid should be allocated, and high pressure fluid should be allocated. And in shell side, condensing vapor until unless it is not corrosive, high viscous fluid and low flow rate stream should be allocated to shell side. So, what is the meaning of this priority? It means I have to first consider corrosive fluid, okay, and then hotter fluid and then fouling fluid, like that we have to arrange. Fine. So, let us say if corrosive fluid has lesser temperature, okay, then only I should allocate that to tube side, and then in that case hot fluid will be allocated to shell side, but that will work because more problem is with corrosiveness than the hot or cold temperature. Okay. So, I have to decide according to this priority table. Okay. And now we will consider some velocity and pressure drop conditions in shell side and tube side. So, typical design velocities in shell side and tube sides are, when I am considering liquid tube side flow rate should be 1 to 2 meter per second, maximum 4 meter per second, and if I am considering water it is 1.5 meter to 2.5 meter per second. Similarly, in shell side it should be 0.3 to 1 meter per second, okay. And if I am considering vapor, we have to consider the velocity in these ranges. Okay. So, these are some permissible limits to handle the liquid and vapor in shell side and tube side, and in the similar line I can consider the pressure drops in shell side as well as in tube side. Okay. So, that pressure drop limits are as per the optimum design. Okay. For liquid, if viscosity is less than 1 millinewton second per meter square, maximum pressure drop should be 35 kilonewton per meter square, and similarly if viscosity changes up to 10 millinewton second per meter square, we can consider this much as the pressure drop range. In the similar line we can consider gas and vapor pressure drops, right. So, when a high pressure drop is utilized, care must be taken to ensure that resulting high fluid velocity does not cause erosion or flow induced tube vibration. So, we have to take care about that vibration should not occur in tubes. So, permissible limit of pressure drop must be maintained along with the velocity. Okay. So, these are some of the guidelines about the design, and all these guidelines we will consider in design of shell and tube heat exchanger. Okay. And these are some references you can go through about detailed study of the basic design parameters, and here we have the summary of the video, and this summary is of the video, and this summary is of lecture 4 as well as this lecture also. Okay. So, in these two lectures we have discussed basic design equation in detail, overall heat transfer coefficient, dirt factor and mean temperature difference. We have discussed FT correction factor in detail, and then guidelines to allocate fluid to shell side and tube side we have discussed, and after that finally we have discussed permissible limits of fluid velocity and pressure drop in shell side and tube side. So, that is all for this lecture. Thank you.